Hi, this is John Whitaker for the graduate level probability class, and this is our 18th video lecture. And today we're going to start chapter 3, and what it's going to have to deal with is conditional probabilities where we're working with random variables. So let's go ahead and get started. We'll start with a definition. So this is chapter 3. Which has to do with conditional probabilities. And as I said, has to do with conditional probabilities, but we're talking about random variables. And conditional expectations. Okay, so as we get started, the first thing we'll do is a definition. It says let x and y be discrete random variables whose joint PMF is f of x comma y. Then, the conditional probability mass function of x given y, is denoted by L sub x given y of x given y, and defined by f sub x given y of x given y equals to is f of x comma y, the joint PMF, over f sub y of y. Okay, where this is the probability mass function for y, the bottom is. Similarly, the conditional probability mass function of y given x is f sub y given x, and it is equal to the joint PMF over the probability mass function of x. We're going to do examples of computing these after I give the idea. All right, so what's the idea? Well, f sub x, the conditional probability mass function of x given y, is really equal to the probability that x equals to little x given that y equals to little y. That's the idea. And so by our conditional probability definition of events, this is equal to the probability of x equal to little x and, so I'll just put a comma instead of an intersection, y equal to y, little y, over the probability that y equals to little y. Of course, this can be represented by the joint PMF as f of x comma y. And here is nothing more than the probability mass function of y of little y. And so that's why the conditional probability mass function of x given y is equal to this definition, so it's easy to understand. One of the things I failed to write in the definitions for the conditional probability mass function of x given y. So in the definition, I just wrote on that. I should have said it's only defined when, so for f's of x given y, it's only defined for values of y where f's of y is non-zero. That's kind of clear from the definition. Okay. So next, let's look at an example. So I think this is an example we've looked at several times previously. So as an example, let's let f of x comma y equal to x plus y over 21, where x is equal to 1 or 2, and y is equal to 1, 2, or 3. And our two problems will be defined for part A, the conditional probability mass function of x given y, and part B will be to find the conditional probability mass function of y given x of y given x is equal to 2. So this time I'll give a specific value, x equal to 2. So for part A, okay, note f of x given y, of x given y, has equal to f of x comma y over f of y of y. So we need to know what f of y of y is. Well, f of y, well, how do you find the probability mass function of y given the joint? What you do is you sum over all its values, so that's from 1 to 2, of f of x comma y. So that would be equal to, so here we got from 1 to 2 of this thing. So that would be equal to, well, when x is 1, we have 1 plus y over 21, plus, it would be 2 plus y over 21, and ends up being 3 plus 2y over 21. So that's the bottom. Yes. So, f of x given y, what that's equal to is that's equal to f of x comma y, the joint, over f of y, and that's going to be equal to, so let's see, it was x plus y over 21, all that over, we just found 3 plus 2y over 21, and so that's equal to, so the joint, so the conditional probability mass function of x given y is equal to, so you flip and multiply, it would be x plus y over 3 plus 2y, where, again, x is equal to 1 and 2, and y is equal to 1, 2, and 3. That's what we have. Let's do a similar type of work for where we're asked to find the conditional probability mass function of y given x, where x is given as 2. So part B was f sub y of x, y given x equal to 2. And so what that should be equal to is f of 2 y over f sub x of 2. Okay, well, let's find the probability mass function of x. And so what is that? That's f sub x of x will be the sum over all y values. So that's the sum as y runs from 1 to 3 of f, the joint, f of x comma y. So let me expand that a little bit. So that's the sum of y runs from 1 to 3. It was x plus y over 21. So let's see what terms are here. This is going to be x plus 1 over 21 plus x plus 2 over 21 plus x plus 3 over 21. That ends up being 3x plus 6 over 21. And so that can be simplified. And so what I'll write is f sub x of x is equal to, so 3 comes out of everything. I think it's x plus 2 over, no, let's just leave it as is. So 3x plus 6 over 21. Now, if we say, what is f sub x of 2, which is what I'm interested in, that's going to be 6 plus 6 is 12 over 21. Now, so f sub y given x of y given x equal to 2, that's going to be equal to f sub 2 comma y. Remember that f sub x comma y was x plus y over 21, so here that's 2. So it's 2 plus y over 21, all over 12 over 21. So what I end up getting here is 2 plus y over 12, where here I can just say y would be 1, 2, or 3. Let me check my work. That's what I got. Good. So we've seen an example now of computing the conditional probability mass function of x given y and y given x. Okay, here's a definition that involves the conditional probability mass function. Use of it. So we're going to let x and y be discrete random variables. Then the probability, and for any, let's say this, A is a subset of R. The probability that X is an element of A, given Y equal to Y, what that ends up being is the sum over all X values in A, such that f of X is greater than 0, of X, of f of x given y of x given y. So you sum the conditional probability mass function over all x values in A, where the f of x, the probability that x is equal to that little x value is greater than 0. You sum that up and you get the probability that x is in that set A when you know that y is equal to little y. That's this definition. And from that, we get the following definition, and that has to do with a conditional cumulative distribution function. So here's a definition. It says, for discrete random variables, x and y, okay, the conditional cumulative distribution function of x given y is denoted by so x given y of a given y and given by, defined by, so x given y of a given y is equal to the probability that x is less than or equal to a, given y equals to y, and that is equal to the sum, if you will, over all x values that are less than or equal to a of the conditional probability mass function of x given y in that fashion. Let's look at an example of that. Okay, so as an example, we'll look at the following. We're going to let x and y be discrete random variables. With joint PMF f of x comma y equal to, so it's 2x squared plus 3y over 202, where x is equal to 1, 2, and 3, and y is equal to 1, 2, 3, and 4. And so part A, I'm going to ask two things. So find the conditional CDF, cumulative distribution function, of x given y. And part B, it's find the probability that x is greater than 1 given y equals to 3. Okay, so we're finding this conditional CDF. So for part A, we want to find f, so x given y, or a given y. And so if we look back at the joint PMF, you'll see that the x values are 1, 2, and 3. And so, remember this is defined, the probability that x is less than or equal to a given y equals y. And so if you say, what's the chance that x is less than, let's say, -2, given y is equal to some number, it doesn't matter what. That is 0 because x cannot be less than or equal to minus 2, because the output values for x are 1, 2, and 3. So what I can say is, for case 1, if a is less than 1, then f sub x given y of a given y is equal to 0. Case 2. If a is sandwiched in between 1 and 2, then f sub x given y of a given y, what that's equal to is the sum over all x values less than whatever a is. And the only x value that's less than a is 1. X run from 1 to 1 of f sub x given y of x given y. So I need to compute this conditional probability mass function. So f of x given y of x given y, what's that equal to? Well, that's f of x comma y over f sub y of y. Note, f sub y of y is the sum over all x values, so x runs from 1 to 3, of f of x comma y. That's equal to the sum, as x runs from 1 to 3, of 2x squared plus 3y over 2 over 2. And so let's see what this is. So when x is 1, we get out 2. So that's 2 plus 3y over 2 over 2. Plus, when x is 2, we get 4 times 2 is 8. It's 8 plus 3y over 2 over 2. Plus, when x is 3, we get 9, we get 18. So it's 18 plus 3y over 2 over 2. Let's see what this is. So there's 10, it's 28, plus 6 plus 9y over 202. That's what my previous work showed. We're good. Okay, continuing on. So, f of x comma y of x given y, not comma y, given y, was equal to 2x squared, f of x comma y over f sub y of y, which equals to 2x squared plus 3y over 202, all over what we just found. We found the f sub y to be 28 plus 9y over 202. And so, f sub x given y is equal to 2x squared plus 3y over 28 plus 9y. Okay, so the conditional CDF of x given y of a given y equal to y, when in the case that we're in that case is when a is sandwiched between 1 and 2, could be equal to 1 but not 2. That's equal to what was the sum as x runs from 1 to 1 of this. Excuse me, so when x is 1, that's 2 plus 3y over 28 plus 9y. And so that's what we obtain. Here again, 1 is less than or equal to a is less than 2. So we need to move on to case 3. When a is sandwiched between 2 and 3. So case 3, here we have 2 is less than or equal to A is less than 3. So the conditional CDF of X given Y of A given Y, that's equal to the sum, and here it's over the X values, they're less than A, so that's from 1 to 2, of the conditional probability mass function of X given Y, X given Y. Well, we just found this. This is sum as X runs from 1 to 2. And this was 2x cubed plus 3y. It's not x cubed, it's x squared. All over 28 plus 9y. So as X runs from 1 to 2, what we get here is 2 times 1 squared, that's 2 plus 3y over 28 plus 9y. Plus, when X is 2, we get 4 times 2, that's 8, plus 3y over 28 plus 9y. That's equal to, just simplifying, so it's 10 plus 6y over 28 plus 9y. So again, summarizing, f of x given y, big F of a given y is equal to 10 plus 6y over 28 plus 9y, where, or if, 2 is less than or equal to a is less than 3. So one more case to consider. So the next case is if A is bigger than or equal to 3. This case 4. Now remember, the X values ran from 1, 2, or 3. That's what they were. So the probability that X is less than or equal to A in this case, given Y is equal to Y, well, all the output values of X are less than this A. So it ought to be 100% 1. Let's verify that. Now, the conditional cumulative distribution function of X given Y of A given Y will be equal to the sum as X runs from 1 to 3 of, it was 2x squared plus 3y over 28 plus 9y. And then that's going to be equal to, so we have 2 plus 3y over 28 plus 9y. When X is 2, we have 8 plus 3y over 28 plus 9y. And when X equals 3, we're going to get 18 plus 3y over 28 plus 9y. And indeed, when you add those up, you get 28 plus 9y over 28 plus 9y, which equals to 1. So here, the conditional cumulative distribution function of X given Y of A given Y, that's equal to 1 if A is bigger than or equal to 3 in this case. Okay, so that concludes our example. I'm not going to summarize this conditional CDF as one form. Just write that down if you like. Just each one of those parts, piece by piece. Okay, the next thing we're going to do is we're going to look at the case where we have jointly continuous random variables involved. So here's the definition, and it's going to work similarly to what we just saw with the discrete cases. Okay? So here we're going to let x and y be jointly continuous. With joint PDF, the probability density function, f of x comma y. Okay. Then, the conditional probability density function of x given y is denoted by f of x given y of x given y, and defined by here it is, f of x given y is equal to f of x comma y, the joint PDF, over f sub y of y. Same definitions we have. And this is for all y's where f sub y of y is greater than 0. Because you can't divide by 0. Okay. Of course, similarly, the conditional probability density function of y given x is f of y given x, which is equal to the joint over the PDF of x. So let's look at an example. Oops. So my example is going to let f of x comma y be defined by 12x if 0 is less than y is less than 2x is less than 1 and 0 otherwise. B, the joint PDF of x and y. Okay, so what do we want to try to find? So part A says find f sub y given x, and part B says f of x given y of x given y. Okay. So here, for part A, by definition, we know that f sub y given x that's equal to f of x given y over f sub x of x. So we've got to find this PDF of x. So f sub x of x is equal to the interval from minus infinity to infinity, if you remember. You know, I don't have enough room. It's equal to the interval from minus infinity to infinity of f of x comma y, and it will be integrated with respect to y. That's what the definition we have. And so here, it's on another board, but the joint PDF is defined to be non-zero only over certain regions. So here, the y values run from 0 to 1. The x values, well, they run from, well, it says that 2x is sandwiched in between y and 1. And so, and y's got to be between 0 and 1. So that means 2x has to be between 0 and 1. So that means x has to be between 0 and a half. And then y equal to 2x is this line. So we're split this rectangular region up into two triangles. And the part where the 2x is bigger than y, I believe that's down at the bottom. Okay, so that's the region that we integrate over, where the joint PDF is non-zero. So this is equal to, okay, so you have a fixed x, like this one. And you ask yourself, where that fixed x, where do the y values run from? Well, they run from 0 to this line. Well, what is this line? It's 2x. Okay, and what is f of x comma y? Well, it was 12x. And we're integrating with respect to y. So that's 12xy evaluated as y runs from 0 to 2x. And so what I get here is 24. So when x is, when y is 2x, I get 24x squared. And when minus, when y is 0, we just get 0. Okay, so f sub y given x of y given x. Remember, that is f of x comma y over f sub x of x. And so that's going to be equal to this guy over the region which is non-zero. It's 12x over 24x squared. So we end up getting 1 over 2x. That's what we have. And so here, this is where you could say, this is where 0 is less than or equal to, I think, 2. So x is bigger than or equal to 0 and less than or equal to 1/2. I think we didn't have the equal to. Yeah, that's what we have. Okay, now for part B, what's part B at? Well, f of x given y, so this is the conditional probability density function of x given y, so that's the next thing was asked for. That's equal to f of x comma y over f sub y of y. So we need to find f sub y of y. Well, that's going to be equal to the interval from minus infinity to infinity of the joint integrated with respect to x. And remember, this guy is 0 most of the time. So where is it 0? Let me write that back here. So if you remember, this was 1, this was a half. We're splitting this, this is 1. And we were looking at this part down here. And so if we said, well, for a fixed y, what do the x values run from? Well, the smallest thing, well, would be this line. Smallest point would be this line. What is this? Y equals 2x. So x would run from y over 2 up to 1/2. And so here, this was 12x, and it's dx. Oh, this was off. It's not going to be that bad. Let's go ahead and compute that. So that's equal to 6x squared. I need to evaluate that from y over 2 up to 1/2. When I stick in 1/2, that's going to be 6/4 minus, when I stick in y over 2, it's going to be 6y over 4. It should be squared. So 6/4 can come out, that's 3/2, and I have 1 minus y squared left over. So that was the probability density function of y. So f of x given y, that's going to be equal to 12x over 3/2, 1 minus y squared. So that can be simplified. Well, 24 divided, it's 8x over 1 minus y squared. And here we have the stipulations that 0 is less than y is less than 2x is less than 1. We've computed the conditional probability density function of x given y. This is part B. Okay, so here's a new definition, similar to the definition we had. It says, let x and y be jointly continuous. Then the probability that x, I should back up, and let A be an element of R, subset of R. Then the probability that x is an element of A given y equals to y. That's the integral for over A of this conditional probability density function of x given y. Okay? And what we're integrating over is with respect to x. Okay? We're integrating over A, but we're doing it with respect to x. Let's do an example of that. We'll use that definition. So, as an example, we're going to say, let U and B be continuous random variables with joint PDF So it's defined to be f of uv is equal to 1/2 uv if 0 is less than u is less than v is less than 2, and it's 0 otherwise. Okay, so what do we want to do? So in this example, we want to find the probability that u is less than 1/2 given v equals to 1. That's what we want to do. So note, to do this, we want to find probability u is less than 1/2 given v is equal to 1. That's supposed to be equal to, by our previous definition, is the region over which u is less than 1 of f of, it will be u given v, and that's not less than 1, 1/2. U given v of u given v equal to 1. And then this would be integrated with respect to u. So that's what we are. So we have to find this conditional probability density function of u given v. Let's work on that. So note, f of u given v is equal to f of uv over f of v of v. Well, f sub v of v, so let's see, that's the integral from minus infinity to infinity of f of uv du. Okay, so remember, the joint probability density function is often 0 in this example. And so when's it non-zero? So let's see. Let's call this the u-axis, the v-axis. The u and v run from 2 to 2. And we have u equal to v, and splitting up that square. And we want u to be less than v, so v's are bigger. So it's these values here. Now, for a fixed v, here's one, we see what u runs from. So f sub v of v is going to be equal to, okay, so the u's will run from 0 to this line, which is, I think, just u, so we're saying to v, of what was the joint PDF. It was 1/2 u times v, and then we'll do du. This ends up being 1/2 u squared divided by 2, so it's 1/4 u squared v. I need to evaluate this as u runs from 0 to v. So I end up getting 1/4 u to the third. That's what this guy is, f sub v of v. So f of u given v that's going to be equal to, so this is 1/2 uv over 1/4 u to the third, and that's going to be equal to, so this will be 2 v over u squared. So f of u given v equal to 1, that part is just going to be 2 over u squared. You know, I made a mistake. What did I let u be? I let u be v. So this is going to be v. So this is a v. So this is 2u. Oh gosh, all this is wrong. 2u over v squared. And so here, when I let v be 1, I'm sorry about that. I was supposed to stick in u equal to v. Okay? So make that change. Make a mistake. So when I do that, here's the result that I get. And so when I let v be equal to 1, I end up just getting 2u. There we go. Okay. Yeah, that's what we get. 2u. That's correct. Okay. So, what are we trying to find? So the probability that U is less than 1/2, given V equals to 1. Remember, that's supposed to be integral of U is less than 1/2 of F of U given V of U given V equal to 1 du. Okay, so I need to describe this. So let me draw the picture again. So I think we had, it was from 2 to 2. U equal to V. This was the region right here. And we're letting V be 1. So V equal to 1 is right here. This is the V axis. This is the U axis. And so here, this is where V equals to 1. And here we said 1/2, right? So 1/2 is right here. So we're only going to integrate over this part of this line. And so what I integrate, that's equal from 0 to 1/2 of this function, which we found, let me see, it's 2u, du. So when I integrate this, I just get u squared, I get 2u squared over 2. That's just u squared from 0 to 1/2. I end up getting a 4. When I stick in 1/2 squared, I get 4. When I stick in 0 minus 0. Let's just get 4. And that's the answer. As a fact, we won't do anything with this currently, but it's something easy that you can prove. If x and y are independent random variables, then either the conditional probability mass function and conditional probability density function of f of x of x given y, that will just be equal to f sub x of x, the probability mass function, probability density function of x. The last thing we're going to do today is talk about conditional expectations, but only in the setting, I think, for discrete random variables. Okay, so here's the definition. It says, let x and y be discrete random variables. Then the conditional expectation of x given y is denoted by the expected value of x given y equal to y, and defined by, okay, so we'll call it like discrete random variable. It's a sum over the x values of x times the conditional PMF of x given y. That's what it's defined to be. Sure I didn't make a mistake, I didn't. There we go. Let's do an example, we'll call it quiz. Okay, so as an example, let's turn to our standard example we've been using. So as an example, we're going to let f of x comma y be equal to x plus y over 21, where x is equal to 1 and 2, and y is equal to 1, 2, and 3, be the joint probability mass function of two discrete random variables, x and y. So here's the directions. It's fine, the conditional expectation of, here I'm going to say x given y equal to y. So we just say it like this, given x equal to y. That's what I'm trying to find. We probably did some of this work already, but note the expected value of x given y is equal to the sum over the x values. So here's 1 to 2 of x times f of x given y, x given y. So for this part, f of x given y, x given y, is equal to f of x comma y over f sub y of y. Well, I'm going to do this again very quickly. F sub y of y is the sum over the x values, the 1 and 2 of the joint. So f of x comma y. And so here I can look at it, I remember now. So it's x, the sum, as x runs from 1 to 2, here it's x plus y over 21, and so that's going to be 1 plus y over 21 plus 2 plus y over 21. This ends up being 3 plus 2y over 21. So f of x given y, that's going to be equal to, it was x plus y, the f of x, well, you write it out, f of x comma y over f sub x, no, f sub y of y, and that's equal to, here, this is x plus y over 21, all divided by 3 plus 2y over 21, and so we end up getting, it's x plus y over 3 plus 2y. That's what I got. So, so the expected value of x given y, that's going to be equal to the sum over the x value, 1 and 2 of x, and then here we just found this part. Oh, my eyesight's not very good. It's x plus y over, I think it was 3 plus 2y. So let's see, when x is 1, that's going to be 1 times 1 plus y over 3 plus 2y, plus 2 times 2 plus y over 3 plus 2y. Let's see what that is. That's going to be 1 plus y plus 4 plus 2y, all over 3 plus 2y, and that is equal to, so 5 plus 3y over 3 plus 2y. So that's what we get. We get some expression for the conditional expected value of x given y. We get some expression in terms of y. That's something to keep in mind. So we could say the expected value of x given Remember what y's ran from. They ran in this problem from 1 to 3. So if you said, well, what's the expected value, conditional expected value of x given y equal 1? That means, what's the average value of x if you know that y was 1? Well, our answer is going to be, if y is 1 here, it's going to be 8 over 5. Also, the average value of x given y equal to 2, well, what's that going to be? That's going to be 6. It's going to be 11 over, here this is 4, it'd be 7. Also, finally, the average value of x given y is equal to 3. They tell you y was 3. What was the average value of x? That's going to be 14 over 9. So, ladies and gentlemen, that's enough for today. Thank you very much for your time and patience.